So I repeat the last video that I'll be discussing now. At thermal equilibrium, P1, so let me write down, at thermal equilibrium between the atomic systems and the radiation field. Thermal equilibrium between what? Between the atomic system and the radiation field, because equilibrium is between two radiation field. What happens at thermal equilibrium between the atomic system, between two different phases, isn't it? There should be equilibrium. So here we are talking about thermal equilibrium between atomic system and the radiation field. All right, what happens? The number of upward transition must be equal to the sum of the number of downward transitions. So the number of upward transitions, probability for the number of upward transition is P12. This is equal to P21 plus P21 prime. That's what we had described, isn't it? P21 plus P21 prime. So now if we put down the Einstein's A and B coefficients, what we have is B12 N1 U nu is equal to A21 N2 plus B21 N2 U nu. Now students, this portion, video number 3, last part of video number 3 and the entire video number 4, Einstein's A and B coefficient is a sure short question for your exam. So this you have to prepare. It's very easy. If you listen now to the videos and if you also practice a little bit, you can do it for your exam. Okay, you can just take out U nu from here to show that this is equal to A21, okay, divided by N1 by N2 into B12 minus B21. Okay, and this actually you can further write as A21 by B21 divided by N1 by N2 B12 minus by B21 minus 1. You can write it in this manner. Now, well, if you ignore the degeneracy of energy states, the population of the energy state E2 of a system in thermal equilibrium is given by Boltzmann distribution law. Maxwell-Boltzmann distribution law. Okay, what is the population? The population of the energy state E2 is given by Boltzmann distribution law. Okay, so what is that? What is Boltzmann distribution law? What does it give you? It tells you that N1 by N2, this is the Boltzmann distribution law, okay, is equal to e to the power E2 minus E1 by KT. Okay, so what is E2 minus E1? In case of photons, it is equal to e to the power h nu by KT. You have seen it in Planck's radiation law, isn't it? What is small k? K is your Boltzmann constant. K is the Boltzmann constant. Okay, all right. So you can write u nu as, you can write this u nu over here that you have written down for u nu, you see. This u nu now, in place of n1 by n2, you can write this as, well, u nu equal to A21 by B21 divided by B12 by B21 e to the power h nu by kt minus 1. See, this is what you are getting for your energy density. Now, doesn't it look somewhere quite similar to Planck's radiation law? Okay, so if you compare with Planck's radiation law, so comparing with Planck's radiation, comparing with Planck's radiation formula, what do you get? What is Planck's radiation formula regarding the energy density u nu? By now you must have practiced and you are quite ready with this. 8 pi h nu cube by c cube 1 by e to the power h nu by kt minus 1. If you compare this with your previous expression, what do you get? If you put this as equal to A21 by B21 divided by e to the power h nu by kt B12 by B21 minus 1. If you compare this with this, what do you get? Well, what you get is the following, that on comparing, isn't it? What do you get? We get B12 equal to B21, isn't it? And A21 by B21 is equal to 8 pi h nu cube by c cube. So these two relations are called Einstein's relations. The coefficient A and B, you can call this as A and this as, you can call this as B. And if this is B, this is also B, then you can call this as A. Okay. So they are called as Einstein's A and B coefficients. Okay. Now the ratio of the number of atoms undergoing spontaneous emission to that in case of stimulated transition. How do you find out that ratio? The ratio that is undergoing spontaneous emission to that which is undergoing stimulated transition. That ratio R is equal to, R will be equal to A21 N2 by B21 N2 u nu. Okay. All right. So if you just find this, you will see this is equal to e to the power h nu by kt minus 1. Okay. So in the optical region at room temperature, this h nu by kt, you can find the value of that. So please find the value of this h nu by kt. Okay, and then you can find the value of the ratio. So, well, it is a large number and so R is also very large. It means spontaneous in the optical region, you'll find, if you calculate this value, you will find that the spontaneous emission is predominant in optical region. So by discuss how the spontaneous emission, how and why the spontaneous emission is predominant in optical region. That's your assignment. Okay, what you have to do over here is just substitute the value of h nu by kt and obtain the value for r. Okay, and show what value you are getting over here. Okay, you will see it is very large. Alright, so it means that the spontaneous emission is predominant in the optical region. So in practice, the absorption and emission process occurs simultaneously. At thermal equilibrium, stimulated emission is not a predominating process. Even for sources operating at higher temperature and lower frequency, spontaneous emission only predominates. So you need very special arrangements to have stimulated emission, which we will discuss in our next class. Let's stop over here. Today you will have just this assignment to answer. Okay, just find the value of R. That is your only assignment for today.